In this video, we're going to be talking about how to combine capacitors and inductors in series. Let's go ahead and start with an inductor. Inductor behaves more or less, when we combine them, they behave more or less like a resistor. So they combine the same way as a resistor. But one thing we have to remember is that not only you have to find the value of L equivalent, you also have to be able to find the initial conditions. So at time t0, what the current is that is flowing through inductor. So that's a big difference with the resistors. Since the relationship between V equal to and I, V equal to L di dt, it's the same. It used to be V equal to Ri, now it's V L di dt. The relationship, the proportionality of which side L is, which side the I is, and which side V is the same. Therefore, the inductor is going to combine much like a resistor would be. So, for example, if we had a number of inductors in series, which means one end is connected and all of them will have the same current. Okay. If you have a whole bunch of these, let's say we have n of these connected from L1, L2, and Ln, and as long as we know that at time t0, whenever that time is, so has some current, this is relatively easy. We just say, okay, in that case, L equivalent for the series case, just like a resistor, is L1 plus L2 plus however many L's are in series, and Ln. I just want to just make sure everybody remembers that two inductors are in series when they're connected on one end and they have the same current, which these do. So this would be series. And the parallel, which pretty much works like a resistor as well, except for the initial condition. So if you've got a bunch of inductors in parallel, so we got, let's say, L1, we've got L2, a whole bunch more, and then we've got Ln. So we've got Ln, L2, and L1. Now each one of these will have its own initial condition. So you're going to have I1 at time t0, I2 at time t0, and In at time t0. So the equivalent, again, the L equivalent in this case, you still would have one inductor that would be equivalent to all of these put together, would have the same voltage across here as you would have over here, and the current that flows here would be the same current that flows here. Okay, in this case, you will have an L equivalent also. You will have an initial current also. In this particular case, we will apply the KCL, and we'll say, okay, the initial current that comes this way is equal to sum of all this current. So first of all, I t0 for the end result is equal to I1 at time t0 plus I2 at time t0 plus In at time t0. Very much, that's a new thing we do for inductors, finding the initial current through them. But as far as the L equivalent is concerned, is very much like a resistor. Is 1 over L equivalent equal to 1 over L1 plus 1 over L2 plus 1 over L, or plus more, however many there are, plus 1 over Ln. So that takes care of it. As you can see, the calculation of the inductor equivalence is identical to what we did with resistor. The one difference is now you have the additional responsibility of having to find the initial current. In the case of series, initial current will be basically the same as the initial current through any other inductors because they're the same by definition. And in this case, it would be the sum of all the current. In the case of parallel, it would be the sum of all the initial current. So So that takes care of the inductors. Now let's go ahead and take a look at the capacitors. Again, capacitors, you always have to also have to worry about initial condition, but there's one other twist is if you look at the relationship between I and V, you notice that I is on this side and V is on the side that C is. So what happens here is that if you want to think about it, the combination of series and parallel for capacitors reverse what we have done for inductors and resistors. So let's take a look at it. So when we have a bunch of capacitors, C1, C2, and a whole bunch more, and then finally last one, Cn, this is plus and minus Vt, this is It. Now remember that each one of these will have its own initial condition, which is V of that time t0, and V2 at time t0, and a whole bunch more, and then of course last one is Vn at time t0. Now what you have to pay attention to when you come over here and do an equivalent, C equivalent, is you have to calculate the initial condition for this thing, which is V at time 0, in addition to the C equivalent that you have to calculate. Okay? So that's called the initial condition. That's just variable over time. So in here, when you have capacitors in series, the series definition is the same. They're connected in one side and the current through all of them is the same, which is the case here. So C equivalent is calculated by 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. Now V of t0, the initial condition for it, is equal to, actually notice the Vt0 is going to be the sum of all these, basically KVL idea. So Vt0 is going to be V1, initial condition for capacitor 1, capacitor 2, and on till the last capacitor. So that's the two things you got to do here, and calculating the C equivalent and calculating the initial condition. Now the next topic here, so this was capacitors in series. So now if you go to the parallel case, we'll see that again it's opposite the resistors. So we're gonna have a few capacitors, we don't know how many, however many. They're gonna have a kind of voltage across them. That voltage creates an I of t, and now you'll have n of these ones connected, and at some point you will have one last one, so you will have Cn, C2, C1, and as you can see these are in parallel. So if I know the initial condition for one of them, then I know the initial condition for all, because they have to be the same. So if I do a C equivalent for this, again, when we're looking in here, and this is I of t. So the initial condition is pretty simple. The initial condition is just going to be what was up there, V of t0. But C equivalent in this case is just simply going to be C1 plus C2 plus Cn. So again, opposite the resistors. And all of that is because the relationship between I and V, C is on the V side instead of the I side. All right. So that pretty much takes care of how you combine capacitors and inductors.